What has mathematics to do with software engineering? Director's cut. By virtue of putting off giving my inaugural lecture for nearly 2 years since I was appointed, I have managed to engineer that I'm giving it within a few months of when I turn 50, and I'm going to take the opportunity to look back 50 years, which fortuitously is about to the beginning of software engineering, and forwards 50 years to about the time when today's undergraduates will be retiring. Now, I'm fortunate, I think, to have perhaps the genetics to reasonably think I may be alive 50 years from now, but even given the recent changes in academics' pension schemes, I expect that I will have been able to afford to retire by then, so I don't particularly expect to be held to account for what I'm saying today. I expect not to be lecturing software engineering anymore. So, caveat there. Going back 50 years, 1966 I was born, and by 1968 there was a software crisis. That's impact. But what do we mean by a software crisis? And come to that, what do we mean by software? Well, for purposes of today, software is the parts of a computer that you can't break with a hammer. So you should be thinking about the program that run the computer, all the various ones, and also perhaps about the models about which we'll say more lately. A software crisis, it turns out, is not just about software and not just a crisis. It's too big to be a crisis in the conventional sense. And the key problem is that making good software is slow and difficult and expensive. And in about 1968, this was becoming clear because of the great advances that were being made in computer hardware. The improvement in computer hardware was exposing software engineering as the limiting factor. So the origin of the term software crisis appears to have been the famous 1968 NATO conference on software engineering, which, by the way, was not the origin of the term software engineering. I, along with many other people, have been guilty of telling students that it was for a long time, so I hereby apologise. In looking all this stuff up, I was delighted to come across this gorgeous set of quotations from Thomas Hay about the sociological nature of that NATO conference. So he accuses the editors of the proceedings of the NATO conference of having themselves coined the term software crisis, because he says that specific phrase doesn't really occur in any of the quoted dialogue between participants. When you actually look back at the volumes, that's really rather an unfair criticism, because it turns out that the term crisis, clearly applied to software, occurs many times in quoted dialogue. But more interestingly, he points out the crucial importance of Edgar Dijkstra, one of the participants there, in both seizing on the existence of a software crisis and identifying the absence of mathematics from the discipline as a key cause of it. So here's what he said at the NATO conference. He says that in the Netherlands they have this term mathematical engineer, and that he thinks is highly applicable to the engineering of software because the basic tools for building software are mathematical in nature, and he's talking about things like abstraction. At the same time, he puts his finger on something which turns out to be a major problem even for us today, which is that understanding that something is important and that some people are able to do it, in this case mathematics, abstraction especially, and being able to teach it are two very different things. Let's pause for a moment and talk now about what we mean by mathematical in nature, and this gives me an opportunity to show you some of my favourite quotations about mathematics. Mathematics may be defined as the subject in which we never know what we're talking about, nor whether what we're saying is true. Well, so far it sounds quite a lot like software engineering, doesn't it? That was Bertrand Russell. My next quotation was said by somebody who wasn't actually a mathematician, and it may be familiar to those of you who are not software engineers, but who have to deal with people who are. Mathematicians are like Frenchmen. Whatever you say to them, they translate into their own language, and forthwith it is something entirely different. He said it in German, which sheds another piece of light on it. Many of you probably recognize this as a quotation originated by Paul Erdős, a mathematician is a machine for turning coffee into theorems. You're wrong. In fact, it wasn't Paul Erdős who originated it. It was Alfred Rényi, but Paul Erdős popularized it. I'm going to take the opportunity to introduce a bit of notation. M, a mathematician, is a machine or a program or a function for turning coffee, and for definiteness we'll say here that C is a set of cups of coffee, into theorems, and for definiteness, here is a set of theorems. So the idea here is that, stretching reality a little, a mathematician is a machine which takes one cup of coffee and turns it into one theorem. I don't know whether I'm going to have anybody in the audience who will be in the intersection of people who will find this joke funny and people who will never have seen it before, but it's my favourite category theoretical joke. In fact, it's the only category theoretic joke that I know. A co-mathematician is a machine for turning co-theorems into phi, and we might notate that like that. Now, of course, in the real world, we're not really so interested in co-theorems, we're interested in theorems. And so what we really want is a machine for turning theorems back into cups of coffee. Unfortunately, there's more information in a cup of coffee in a theorem, so you can't do that. But what you might be able to do is to take an old cup of coffee and a theorem and produce from it a new cup of coffee. This may be familiar to many of us in the guise of taking a hot cup of coffee and a false theorem and producing out of it a cold cup of coffee. If you're really lucky, it may happen the other way round. You may take a hot cup of coffee and a false theorem and produce out of it a true theorem. And we can regard this, if we like, as the process of restoring consistency between a pair, a cup of coffee and a theorem, which are in an inconsistent state. And that makes sense given this definition of consistency, in which we say that a cup of coffee C and a theorem Th are consistent, provided that either the cup of coffee is cold and the theorem is false, or, the more happy state of affairs, the cup of coffee is hot and the theorem is true. And we'll come back to this later on. But seriously, folks, let's go with mathematics is the study of patterns. When I looked up to see who said this originally, it turns out just about everybody said it. We get about 26,600 results for that phrase in quotation marks from Google. Okay, so software is chock full of patterns, so this looks good. Maybe software engineering is a branch of applied mathematics. Dijkstra was right, and that's the first answer I want to give to the question that I started the lecture with. Let's get back to our chronology. 1976, I was 10. I wanted to be a mathematician. Those were the patterns I was most interested in at the time. And in contrast to the rather academic NATO conference, which has been criticised by Haig and by others, this was one of the kinds of things that was coming out of the practical application of computers. My father wrote a book, Computer by the Tail. Now, this is a book aimed at managers who are managing the introduction of computers into an organisation. Some aspects of this book now seem extremely dated. A computer man is often much more concerned with techniques than their application. But some of it appears sadly undated. He is a poor communicator and a worse listener. He is not over concerned with schedules or budgets. He is largely ignorant of the business you are in. And with introducing a computer into an organisation, as with so much of introducing technological advances into organisations, we find all too often the areas which were not giving problems have been improved. They are easier to improve, but the real problems tend to remain. I can't move on without pointing out momentarily that this gave me my first appearance in print in a case study in this book. Here's something you're more likely to be familiar with, published in 1976, the seminal paper by Peter Chen introducing the entity relationship model, and I'll have more to say about this later on. Between 1976 and my next 10-year stopping point, 1986, I nearly defected to physics, thanks to this truly excellent teacher. I was fortunate to be taught by many excellent teachers during my time, both at school and at university, but Mrs. Perry stands out for me because she taught me so many things that have proved to be important in my dealings both with mathematics and with software engineering ever since. In the context of school physics lessons, we talked about problems that had multiple ways in, which was something of a novelty because in mathematics at school, usually there was one right way in, and if you didn't find it, you'd just done it wrong. She talked about how to handle uncertainty in what you were doing in your problem, and how to pick an explicit abstraction, explicit in the sense that you understood what you were abstracting away and why, that you could understand what you didn't, you could identify what you didn't understand already, and perhaps even write it down in little notes, and make explicit what your options were for proceeding with a problem. And some of the techniques that she taught me for handling those things, such as writing little notes to remind yourself of what it was that you were uncertain about, are things that I continue to try to teach my students to this day, and I'm very grateful to her. I didn't, however, defect to physics. I went off to Cambridge to read maths. By 1986, that was my window up there in the highest point of that building. There was a software crisis, but I was ignorant of it because I had only been offered one course that had anything to do with computers. I went along to its first meeting. I understood not one word, and I didn't proceed with that course. But I did learn lots of other things in Cambridge, and here are some of the people to whom I'm particularly grateful from that time. Martin Hyland is known to many of you and is remarkable for the sheer number of female, especially, mathematicians and computer scientists he's been influential on over the years. Keith Kahn was my director of studies, that's the equivalent of our personal tutor role at Edinburgh, for most of my time at Cambridge. As I sometimes tell my personal tutees, I was anything but an easy undergraduate, and I'm very grateful to Keith for helping me to get through more or less in one piece. Two of my fellow students, Julian Bradfield and Graham Wheatman, were extremely influential on me, both personally and mathematically. Julian Bradfield, many of you know. Graham Wheatman you'll be less familiar with. Elsa Gunter, many of you will know because these days she's a distinguished professor in theoretical computer science, but in those days she was giving supervisions, we would say tutorials, in representation theory. Now, Elsa was, as far as I recall, the only woman who taught me in any capacity during my 3 years at Cambridge, and she taught me representation theory, and I went on to do my PhD in representation theory. You might think that's coincidence. I might have a bridge to tell you. I went off to Warwick to do my PhD in pure maths still, and about Sandy Green I will only say that if I ever manage to be half as good a PhD supervisor as he was for me, I shall consider myself very fortunate indeed. I was considering the structure of different mathematical structures during my PhD, and that's one of the diagrams from my thesis in the background. But once I finished my PhD, I had the strange idea that I wanted to do something that would influence the real world, and I went off to work as a software engineer at BT in the Glasgow Systems and Software Engineering Centre, and started considering a different kind of structural diagrams. Those are Booch cloud diagrams in the background. This is Tony Hall, about whom I will only say that I know full well that I will never become half as good a manager as he was. It's a real pleasure to be managed by somebody who's really good at management. At this point I'm going to stop thanking people individually because I reach Edinburgh and this becomes invidious. But before I move on to how I reached Edinburgh, let me say a couple of things about what I learned as a software engineer in BT Glasgow. When I arrived, I spent the first 18 months of my time working on a very large project which had at that point been in progress, had used up hundreds of person years of time, and I worked on it for 18 months. And then the project was cancelled, and it was a classic instance of the kind of thing that was happening in the software crisis at that time. And one of the things it's done for me is to give me a very valuable perspective on times when, as an academic, you might spend several weeks not getting anywhere, failing to prove a theorem, because the amount of time lost in apparent unproductivity in that kind of situation completely pales into insignificance compared with the amount of time that ultimately produced nothing in a large cancelled software project. But I learnt many other interesting things, and among them was the importance of modelling and object-oriented software. I was fortunate to be able to come back to Edinburgh as an academic, and so by 1996, here I was lecturing software engineering, and there was a software crisis, and in those days, if you said to a group of first-year students, "Have you heard of the software crisis?" all the hands would go up. This was common knowledge. In 1996, this Dagstuhl meeting on the history of software engineering was held, and one of the things that was talked about there was the software crisis and the apparent lack of any clear expectation that it would finish anytime soon, because although software engineering was improving, steadily increasing requirements and ambitions had helped to sustain it, and it still wasn't clear that it was even sensible to talk about engineering software. At the same time, though, the rise of modelling in software engineering was becoming important, and it was just the year after that that I wrote the first textbook on the unified modelling language, which was the successor to languages like the Booch notation that you saw in the background of my BT slide. I didn't have a version of this slide in the first practice of my talk, and I got told off for it, so there you go, that's my book. Life moved on, and by 2006 I was doing many different things. Many of them had to do with games. Many of them had to do with my son Robin, who turned 3 that year. Some of them had to do with both. And there wasn't really a software crisis anymore. So what had happened? Now we could argue about the validity of Google's lovely Ngram software, but it's very beautiful. This shows you the frequency over time of a specific phrase, in this case software crisis, in a corpus of books that Google is examining here. And so we see that the software crisis essentially began in about 1968, rose up until about 1990, and then has been falling ever since. Why is that? Essentially, it's because we learned how to engineer software. There were two major advances starting around 1990-1995 in how we do the engineering of software. One of them I've already started alluding to. It's the use of models in software engineering. I'm using here the phrase model-driven. I could have used others. And the other is the rise of Agile software development, and I'll say more about those later. Those of you who know me well would not expect me to pass up the opportunity to mention a couple of non-contributors to the fall of the software crisis. Correlation is not causation. Well, not always. So here we are in 2016. Students have no longer heard of the software crisis, and yet not everything in the garden is rosy. We have headlines like this one about an IT skills shortage, and I love this picture, but it's about the ever-increasing proportion of jobs that are to do with software. It's a seller's market, and it's hard to recruit software engineers. It's almost harder than anything else, apart from this computer game character who's apparently particularly hard to recruit. So we need to increase the supply of software engineers by doing things like teaching our 5-year-olds how to program. In conclusion, Parce Dijkstra, software engineering is more than mathematical engineering. Solving the software crisis required some new ideas, agile development and model-driven development. But now we understand how to build software essentially, and so the only remaining problem is that we don't have enough software engineers. So we need to teach programming in school and fund lots of software engineering students, and we'll fix that. Are there any questions? I lied. Below some of those headlines, we find a more nuanced story. We find people saying not that they don't have any applications for their software developer roles, but that they don't have applications from enough, quote, really talented, unquote, developers. And at this point, I should also confess that when I asked Google to complete how to recruit for me, I was logged in as me, and you might perhaps think that Google, having watched my every move over the last several decades, might have some idea that software engineering is something of interest to me. Another piece of evidence, although the unemployment rate among CS graduates, I think this is 6 months after graduation, is not very high, it is higher than the rate in many other disciplines, which is somewhat surprising. It's true that there's high demand for very good CS graduates. They command particularly high salaries, so not everything I said was a lie. And indeed, what our students can do these days, for example, in their final year projects, is amazing, particularly compared with what was being done in the same kinds of projects, the same kind of amount of time 20 years ago. But we have a problem. The perception is, at least, that too few software engineers have all the skills that are necessary. And there are many opinions on why that is, and I'm quite glad to be giving this lecture before rather than after Sir Nigel Shadbolt's review about this comes out. But we may say at a high level that there are two fundamental possibilities. Either talent is innate and we just need more potential software engineers to choose from, and that's what justifies things like getting our 5-year-olds coding and graduating more students the whole time. Or you might think talent is taught, and the problem is that universities just aren't teaching the right things. If only the wicked universities would teach your favourite silver bullet, everything might be much better. Now, an observation that I can make just from many years of watching students is that software engineering success is at least correlated with success in mathematics. It turns out that the ability to reason, abstract, think computationally is the fundamental sine qua non for being an excellent software engineer, and this essentially is mathematics. The problem is that talented developers need both that and all these other skills. They need to be expert at using current technologies and understand business and have soft skills like presentation skills and whatever anybody else thinks is important at the time. Now, if the limiting factor is maths, as I think it is, then we have a software crisis indeed. Because here at Edinburgh we are fortunate to be able to recruit very strong students from across the world, and they are very good at maths, and even so, many of them struggle with mathematical thinking. It hardly matters whether this ability at mathematical thinking is innate or taught, because either way, we aren't going to be able to improve it radically by an order of magnitude or more now. We might manage a factor of 2, particularly if we manage to address our appalling gender bias, but that's about the best we're going to be able to do. So as long as skills in mathematical reasoning are part of what's needed, the talent recruiters want will never exist in the quantities needed. We can't solve this software crisis by growing many more mathematical engineers. We need fundamentally to change the game. So to see how we are going to do that, let's go back in time as far as 1902 and consider a rather comparable recruitment crisis. So these ladies here are telephone operators. They are connecting early subscribers to the newfangled technology of the telephone by plugging physical wires into different holes in this switch bank behind them. Let's look. In 1886, there was the beginning of the telephone crisis. I had great fun tracking down these attributions. This is my favourite of several possibilities. William H. Preece, the engineer-in-chief of the British General Post Office, which was the predecessor of BT, said apparently in 1886 that if the growth of telephone subscribership continued, by the year 2000, every woman in Great Britain would have to be a telephone operator. That problem had actually come up rather fast. 10 years earlier, he had opined that the telephone might be all well and good for the United States, but it would never catch on in Great Britain because the country has an adequate supply of messenger boys. I think that's lovely, and one can make some kind of parallel with people thinking we don't really have a software engineering recruitment crisis right now, I think. Fortunately for me, though, Preece was wrong both times. The telephone did catch on, and I did not have to go and be a telephone operator. Why not? Because instead we invented the automatic telephone exchange. This is a Strowger exchange at Catford, UK, and some of these were still in use in 1991 when I went to work for BT. It was actually patented back in 1891. By 100 years later, we have things more like that. It's a broadband exchange. And so when I went to work for BT, I went to try to solve the software engineering recruitment crisis, not the telephone operator recruitment crisis. So we solved the crisis in recruitment of telephone operators. Can we do the same with the crisis in recruitment of software engineers? Can we save our 5-year-olds, in other words, from having to be programmers, or worse, mathematicians? So to see how we might do that, let's go back to this picture I drew, in which I claimed that these two developments in software engineering were essential to solving the first software crisis. What do we even mean by software engineering? So I love this quote from Jochen Ludovic, and it's not an accident that this comes from as far back as 1996. He compares software engineering with self-contradictory phrases like threatened by peace or deafening with silence. And when you look at the definition he was criticizing, you can see his point. The idea that we should apply engineering to software is not a definition, but a goal. Why is software engineering hard, even compared with other aspects of engineering? Well, fundamentally, I think it's about uncertainty. It's about the fact that while humans are really good at imagining one course of events, one thing, then the other thing, then the next thing, they are very bad at reasoning about large trees of possibilities, and we have lots of these in software engineering. And especially because of the very softness of software, we have to be able to reason about change. We have to be able to think about what the customer will want next week. Modelling contributed to this by helping us to identify ways to represent the things that don't change that much, to use relatively stable abstractions. Here is an entity relationship diagram, doesn't really matter what that is, from that paper. The key thing I want you to notice about this is that the main rectangles in this are named with the kinds of concepts that are going to exist within a manufacturing firm, even if its precise requirements for software change. Incidentally, notice that this paper already did some model transformation, if you like. It also showed how to derive a data structure diagram from an entity relationship diagram. We'll come back to that too. So although modelling, like object orientation, goes back to the 1960s, if not before, they boomed together in the 1990s, where they supported the capability to do abstraction, to separate concerns in software engineering, and to structure the software around relatively stable things. The current buzzword is model-driven development. Let me broaden out the definition of modelling a little. You've seen a couple of examples, but what do we really mean by a model? This is my favourite one-sentence definition. A model is an abstract, usually graphical, representation of some aspect of a system. And we should admit that modelling is already useful even if models are completely informal, drawn on a whiteboard or whatever. But model-driven development is software development in which models are important and are accorded parity of esteem alongside the source code that comprises the software. And the idea of model-driven development is precisely this separation of concerns that lets us manage information overload. It lets us provide representations that are suitable for each set of decisions so that people can make those decisions without being distracted by unnecessary details. So today, people who embrace model-driven development are typically building graphical models in modeling tools, and those things may be in a general-purpose modeling language like UML or SysML, or they might be in a domain-specific modeling language, a language usually simpler but specifically adapted to their own needs, which might be graphical or might be textual. It's important to realize that models don't have to be graphical. Even the source code of the system itself or parts of it can be considered to be models. They may be generating code from their model, usually not complete code generated from a diagrammatic model, usually more often skeletal code that will then be filled in later by a programmer. They're quite likely to be doing analysis or documentation at the model level, and that's helpful because it makes things feasible that would not be feasible if you tried to do them down at the level of the full source code of the system. And they may be doing some round tripping. Now, what we mean by round tripping is this. Suppose you start with a graphical model and you generate some skeleton code from it, and now you go into your skeleton code and you fill in the details, for example, the details of what you want this particular function to do, and in the process you change some of the skeletal code in such a way that the code is no longer consistent with the model you started with. Now, round tripping is when you're able to press a button or whatever and say, now please update the model so that it's consistent again with my current state of my code, so that you restore consistency by now modifying the model that you first thought of. Now, tools for doing this have existed since the 1990s, but even today they're not very good. What typically happens is that you have to become intimately familiar with the quirks of your particular round tripping tool if you want to use that successfully, and that's a real problem. In the ideal of model-driven development, each stakeholder, for example, each type of user of the system or each expert in a particular technical domain, works with a model that shows only their concerns, and when their requirements or their solutions change, they change their model. Code is generated from the models. All this verification and validation and documentation happens at the appropriate level, at the level of the model that has the information needed for it. So far, it doesn't work very well. Model-driven development enjoys limited success. It works best in well-understood, predictable development processes where typically only one model changes at a time, so you don't have major round-tripping problems. Why is this? Well, fundamentally it is round-tripping. It's the difficulty of keeping codes and models synchronized. Here is a bunch of quotes from a number of papers which have recently looked empirically to why model-driven development succeeds or doesn't succeed. This is not the only problem. People also complain about things like the costs of the model-driven development tools, but it is the problem that comes back again and again, and it's the one problem where if we made a real difference, it would fundamentally change the world. There's a striking similarity between the state that the world was in trying to introduce computers in the 1970s and the state we're in today trying to introduce MDD in the 2000s, 2010s. Here's a typical quotation from one of the empirical papers. Looking at comparative studies gives results that vary between a moderate loss and a moderate gain, but with tantalizing hints that some companies are managing to achieve much higher productivity levels and sometimes not even wanting to talk about it, partly for fear that they wouldn't be believed and partly perhaps for pricing reasons. We said that this is largely because of the difficulty of structuring the development process and predicting it well enough. Well, the other movement that I wanted to talk about, Agile development, has taken as its main focus of concern the issue of how you can alter the software development process so as to understand it better and embrace change with greater flexibility. It's about structuring the development process around the customer's priorities. And in contrast to model-driven development, which is about managing information overload, Agile development can be seen as managing information poverty. We're saying, okay, we don't have all the information that we want so far, but we need to be able to start and do something anyway. And we want not to be thrown by the fact that half the information we do have is probably wrong and we don't know which half. Agile development too has its problems, which I'm not going to go into, but these ones are particularly widely appreciated these days. But suppose that we could combine the advantages of both of these things. Suppose we could take the separation of concerns from model-driven development and keep pace with the real world in the way that Agile allows. I love this quotation that James McKenna pointed out to me. The art of progress is to preserve order amid change and to preserve change amid order. So we need progress in software engineering. We should be careful what we wish for, because currently model-driven development requires you to be essentially a mathematician, requires you to have a deep understanding of the semantics of your non-deterministic modeling language and of your model transformations. And Agile development requires you to be an ace programmer and neither leaves space for you to be expert at something else, for example, the domain or security or whatever it is. And current attempts to combine agility with model-driven development threaten to require you to be both, and that's not necessarily an improvement. So let's talk a bit about how things might be different. Now, I am going to start with a disclaimer. I'm talking about 50 years in the future here. I'm not talking about what we can do within 5 years. 50 years ago, people certainly did not foresee today. But let's think about this a moment. The hard parts of software engineering are requirements and maintenance. I don't work on either of those. Why not? Fundamentally because mathematics has no attack there, and I really think that academia doesn't have much attack there. Can we turn that problem round and take a different approach? Suppose software experts didn't have to understand customer requirements, but instead what software experts did was to understand the kind of things that these customers have requirements for. And suppose that customers then did their own maintenance. That, I think, should be the ultimate vision of Agile model-driven development. So suppose that in 2066 we have some kind of software development environment like this. We have groups of stakeholders in the software. Perhaps our red people are one group of users of our software system and our blue people are another group of users of our software system. And they're each working with models that describe their own concerns, their own requirements. And we probably have other expert groups. Down here in the bottom left we have the purple people. They're mathematicians, you can tell that from the Greek letters, and perhaps what they're doing is they are modifying the required safety or security properties of our systems. And these models are all automatically reconciled and knit together and turned into deployable software which can be deployed to these brown people sitting at their terminals in the bottom right, whatever terminals will look like in 2066. And it's all in the magic of the multicolored wires. That's what we want. Unfortunately, it's really, really hard to write those wires. They're called bidirectional transformations. They have the job of reconciling these models that people are simultaneously modifying. So we really need better languages and tools to support the development of those wires. Well, let's see what we can do. A unidirectional transformation generates one model from another. It might be, for example, generating our skeleton code from our graphical model. And we're pretty good at that these days. We've got fairly decent languages to express unidirectional transformations because these are just programs. We've got more than 700 programming languages, we know. The problem here is that when we change our target model, we're stuffed. We can produce our theorem from our cup of coffee, but if we want to produce a cup of coffee from a theorem, there's nothing we can do. So what we need in order to handle reconciliation between different models, for example round tripping, we need bidirectional transformations. And they need to be able to, in the simplest possible presentation of many, they need to be able to check consistency. They need to be able to say this cup of coffee and this theorem, are they consistent? This UML model and this body of Java code, are they consistent? And if they're not, they need to be able to restore consistency. We need to be able to say we'd like this one modified or that one modified, and it might be that we want a bit of both, but I'm not going to go there today. And we want sensible behavior out of this. At a minimum, we want that consistency restorers really do restore consistency, and we probably also want that if you give a consistency restorer a pair of things which are already consistent, then the consistency restoration process should do nothing. That's correctness and Hippocraticness. So we have two intertwined problems. We have understanding in more detail than that what a bidirectional transformation should actually do, and then we have the problem of how we can engineer confidence that it really does that. We can, of course, write those three elements of a bidirectional transformation, R and R forward and R backward, as separate programs in a standard programming language. But the problem with that is it gives us lots of duplication because all three of those programs have to walk over the structure of the models. And so really, in order to avoid being horrendously inefficient and error prone, we want to have a single artifact that expresses all three of those aspects. And that's called a bidirectional transformation language, a books language. And we have languages that can express books, but we have no good ones yet. We have some fairly good ones and some really terrible ones. Let's not go there. A very mundane problem is that even in the better of the languages we have, they have no facilities for allowing you to do a bunch of things that you definitely want to be able to do, such as handle non-determinacy and handle interaction with the user, for example, to allow the user to express a preference between two different ways of restoring consistency that haven't been chosen between in the books itself. And some work we've done recently here in Edinburgh has been exploring how to use monads and monad transformers to enable future books languages to do that better than they do today. But to look further up at more general aspects of how we can understand how to do repetitive or circular or tree-like reasoning about bidirectional transformations, we have to return to the fundamental issue of why software engineering is hard. It's all about these trees of possibilities, and in some cases, so in particular in the first two of these, handling uncertainty about data input and about interactions, it turns out that verification games have been remarkably successful. Now, this is actually where I came back to academia. I came back to work with Colin Sterling, who had a model checking algorithm expressed in terms of games, and my first task here was to implement that in the Edinburgh Concurrency Workbench. The way this works is like this. If you want to show that some property always holds, you can set this up as a game between two players. Verifier is a player who wants to show that the property does hold, and Refuter is a player who wants to show that it doesn't. And the way it works is that Refuter repeatedly challenges in whatever ways we want to allow as legitimate challenges, and verifier has to be able to meet those challenges on behalf of the system we're trying to check. She has to be able to show how the system will behave correctly in the context of particular challenges from the environment or from its users or whatever it may be. And it turns out that you can, in a very nice formal sense, show that the system is correct if and only if verifier can win that game. That works with a fixed idea of what property we're trying to show. In software engineering, we tend not to have a fixed property. That tends to be the whole problem, that the requirements themselves are uncertain. And so the next step beyond that is to design the game itself, to say, can we refine the requirements and the design together in a process which can itself be seen as a game, as an exploration game. And that game stops when both the requirements and the design are precise enough for our purposes and they are consistent. This idea was explored by my first PhD student, Jennifer Tenser, and there's a journal paper that we wrote together out of that work. We didn't follow that idea up as energetically as I now think we should have done, because Jennifer went off and worked doing software engineering in the real world, and I got interested in other things. But it is, I think, highly applicable to model-driven development problems. Can we combine these ideas to handle uncertain future requirements? I think we might in the future see that specifying a bidirectional transformation is designing a game. So we will design our game by saying we'll design our domain-specific modeling languages. Now, these are the kinds of requirements that our group of users will have for the system. It's the language in which they can express their requirements. and we design a definition of what it is for multiple models in these languages to be consistent, and we say what properties we want of consistency restoration. I'll come to that in a moment, but at least we probably want correctness and Hippocraticness. And then to write a bidirectional transformation is to design a winning strategy according to that game, is to explain how consistency will actually be restored concretely. Then to apply our bidirectional transformation should be to move according to that winning strategy. And some early steps in that direction are these papers that I've written jointly with Julian Bradfield, exploring the semantics of the QVTR bidirectional transformation language. But we need to take it up a level, because those were in terms of specific pairs of models, and I think we need to move it up to be talking about pairs of modeling languages. Some work that's been done already, rather than now talking about work that we want to do in the future. Properties of bidirectional transformation languages, properties of consistency restoration, have received a great deal of attention from us and from other groups recently, because it turns out that correctness and Hippocraticness are not enough to rule out really weird behavior. And the best analogy I can come up with here is the story you may have heard about the hypothetical AI entrusted with looking after the welfare of the human race, which observes that the overall happiness of the human race is negative, and deduces that therefore the best way to improve the situation is to wipe out the human race. It's perfectly logical and definitely not what you want. In order to rule out that kind of behavior, we really want some kind of principle of least surprise. Behavior like that is very surprising. We don't want our books to do it. And we think we can make progress by considering reasonable behavior in senses that mathematicians have long understood. For example, Hölder continuity looks very promising right now, and other things I don't have time to go into, but there's a paper discussing some of these ideas. I'm going to jump over this. It's what you'd expect. We'll need lots of ways to check that our books really are correct. I'm going to jump over this. Everything is multi-core these days. Parallelism is certainly going to be an issue, and we're going to have big models on which a large amount of computation has to be done. And if we want to stay agile, the books might well change while the consistency restoration is being done, and that's going to pose a large number of problems that we've not even begun to address yet. But I'm going to skip over that to address something you might be thinking of as the elephant in the room. I've been talking about models as formal artifacts, and I've been proposing a future in which people who are not software experts are the ones who modify those models in order to express what they mean. But does that not mean that essentially I am asking them to do programming and to think mathematically, which is exactly what I started off saying it wasn't reasonable to expect people to do if we also wanted them to be able to be experts in the domain? Well, it's a legitimate question, and I don't know the answer yet. I do have some hope that perhaps it may turn out not to be a problem at all. It may be that if the model we give people does a sufficiently good job of really expressing only the things that they already know they have to think about, it might not feel like programming. And it might be that our system itself can be clever enough to work out or elicit from the domain experts what it is they really want. And the best parallel I can draw here is between the early days of web searching. So I've said 1996, but I probably mean even a couple of years earlier than that. Do people remember Alta Vista? Some of you do, I'm sure. In those days, it used to be hard to find what you were looking for in the World Wide Web, even though the World Wide Web was small compared to today, because you had to essentially write complicated Boolean expressions, saying, I want a document that contains this word, but not that word, or that word and the other word. And that was really hard for people to do if they weren't mathematicians. And I remember, probably not as late as 1996, but 1994 certainly, having discussions with people in which I probably even argued, was certainly prepared to entertain the argument, that the World Wide Web would never take off because people would always find it too difficult to write those Boolean expressions. Well, of course, they didn't. We didn't get better at teaching people to write Boolean expressions. We didn't give them great interfaces for writing Boolean expressions. Instead, Google came along with PageRank, and that problem just went away. And I think some of these problems with helping people to be able to write models that say precisely what they mean and what they want from their software might go away in a very comparable way. We also have to bear in mind, of course, that our domain experts might be wrong, or they might even be malicious, and so solutions will be required for that. So, in genuine conclusion now, what has mathematics to do with software engineering? I think I've given you 3 answers to this. I think we can certainly argue that software engineering is a branch of applied mathematics, provided that we acknowledge that the devil's in the application. The application is often the hard part. I think pessimistically, the difficulty of doing mathematical reasoning, especially the difficulty of doing mathematical reasoning as well as being able to do all the other things that software engineers need to be able to do, is fundamentally the reason why it's hard to find enough good software engineers today. It's why we have a software engineering recruitment crisis. But more optimistically, I believe, and I hope I've explained to you something about why I believe, that mathematics may be what will allow us to widen participation in the building of software in future. I want to give a special thanks to my colleagues on the project A Theory of Least Change for Bidirectional Transformations, Faris Abu Saleh, James Cheney, Jeremy Gibbons, and especially James McKenna, with whom I've worked most closely and who has been helpful in the preparation of this talk. I want to thank my friends and family and everyone who continues to teach me, especially my students.